I am Yael. I'm a product owner at SCIA. I am responsible for the developments for all materials inside SCIA Engineer except for the concrete parts. And this webinar today will be about all of the rules that we use inside the steel code check for SCIA Engineer that are not from inside the actual Eurocode. Or at least that's what I was trying to do, because there are a lot more of them than I anticipated. I think we will cover about 95%, leaving only out some minor details. But yeah, I'm forced to try to keep it under 50 minutes. So it will be already a long enough ride without those final extra details that we will miss today. Good. Oh, wow. I'm so sorry again. Next slide. Good. So GoToWebinar. Now that I managed to properly use it, let me explain to you guys how to use it. You guys are muted during this entire presentation. That doesn't mean that you cannot ask your questions. So anytime a question pops up into your mind, just type it into the question box. My colleague, Peter van Tendelo, he's here to reply to all of your questions while I'm speaking, and I will also cover them at the end of the webinar. Also, if after 30 minutes you get tired of all the formulas I'm throwing at your head and you have troubles following, don't worry, the webinar will come onto our YouTube channel after this presentation, so you will be able to rewatch it and restart it at will. So, why would we use rules from outside the Eurocode? Well, sometimes the Eurocode just doesn't offer us a complete guidance on how to calculate every single part inside it. Like, for example, it would tell us to use M critical, but not tell us how to calculate this critical moment. Or, well, the Eurocodes, they have been written now some time ago already. And since then, there has been some research done and some improvements found. And we would not want to keep them for you. So we would like to give you the option to incorporate the recent research results into the check of your materials and of steel in this particular case. This brings us with a very logical follow-up question, which is it actually allowed to use rules from outside the Eurocode? And for this, we would like to reference to the guidance paper L on the application and the use of the Eurocode, which states that the Eurocode indeed sometimes omits some design guidance, like calculating in critical, and that they consider there is available established sources, and that those sources and publications can be used as long as they are giving non-contradictory complementary information. So information that adds to the Eurocode and doesn't contradict it. Okay, this is going to be quite a long webinar. I have split up all the topics into 3 parts. First, we will talk about the additional rules in section classification. Then we will go to the section check. And finally, to the stability check of the members. Let me just check out the question box to see if everything is fine. Okay. It seems like everybody's hearing me, and some would like me to speak a bit louder, so I will try to do that. Good. So let's do a quick recap on what section classification is and what the rules are inside the Eurocode. So our classification defines when local buckling will occur inside a section. If it occurs before we can reach the elastical resistance moment, then it is a class 4 section. If we are between the elastic and the plastic moment, when local buckling occurs, we have a class 3 section. And if we are above, we have either class 1 or class 2, depending on whether a plastic hinge can be formed. How are these sections classified into those classes? Well, that's given by the little tables in the Eurocode, and these show us that it depends on whether we have an internal or external compression element, on the ratio between the length and the thickness of the element, on the yield strength, and on the stress distribution, or more importantly, the location of the neutral axis inside the section. And on that last one is where our first point comes into play. What is this position of the neutral axis? Because we can have it, of course, from the elastic distribution pretty easily. But if we are looking at failure of a section, we want to have plastic stress distributions, and this will shift the position of the neutral axis. So inside SCIA Engineer, you actually have 3 methods available to you to choose the determination of this neutral axis for the classification of your section. The first method is the most commonly used one because it is fast and it is easy also to hand calculate. We just look at the elastic stresses inside the section, or if the moments are small enough, we assume that it is uniform compression. With some added rule that we have here coming from the Semicomp Plus research, of which I will talk to you a lot more later, which gives us some more advanced formula on calculating the stress distribution for doubly symmetric I sections. But it is still not a fully accurate plastic calculation. Why? Because we will only increase the moment inside the section to reach the full capacity, whereas for an actual plastic calculation, we should increase both the moment and the normal force to reach the maximum capacity. And I will have a little sip of water before I go to the next slide. Oh, I had one more point about this slide. That is that the rule about the doubly symmetric I sections will also be inside the next generation of Eurocode. So soon it will no longer need to be in my presentation. A next way to tackle this issue is to find the actual plastic stress distribution and the location of the plastic neutral axis inside our core section. For this, you have the method 2 inside SCIA Engineer, yield surface intersection. What we will do is we will try to find different points on the yield surface of this section, so different combinations of the moments in both direction and the normal force where the section reaches its maximal distribution of stresses before failure. And after calculating all these points, we can kind of form this yield surface. Then we will take our actual combination of forces and we will extend the line until it intersects with this cloud of points. And the point of intersection will give us a location of the plastic neutral axis for this section. Of course, since we don't calculate the full surface, but only a discretization of the surface, it will not be entirely accurate, and we can get some small deviations from the actual position of the plastic neutral axis, but they should be really small deviations. The advantage of this method is that, well, it's slightly slower than the elastic one, of course, because we have to still calculate this cloud of points instead of just bursting out the formula. But we can save this cloud of points, and then for any next combination of forces you will have, you will be able to reuse the already calculated points, and it will go rather fast. The third method we have is for the full-on exact people that want to find the exact correct position of their plastic neutral axis. They don't want to allow for any small deviations. Then we just iteratively go and refine the plastic surface until we find the exact spot of our exact combination of internal forces. Of course, this is much slower, and for every different combination of forces, it will have to be repeated. So what's this difference between using elastic and plastic design? What kind of difference can it give to my classification? For this, I want to take this very simple example of just an I section with one moment component and one normal force component. If we look at the location of the elastic neutral axis, it sits at about 0.63 here. If we use the formula for the doubly symmetric I section, where we increase the moment until we reach the limit capacity, that means we go straight up from the black point on our diagram until we reach our curve, we get a position of 0.77 for our neutral axis. And if we look at the actual plastic redistribution, where both the normal force and the moment get increased proportionally, we actually reach the true plastic neutral axis at a position of 0.83. That means that about from the moment with the my, we do have, let's say, 10%, a bit 6% of the section more under compression than before. So this will give us, a bit worse results, but they're also closer to reality. So it's all depending on what you want to use and where you want to stand on this. SCIA just offers you this choice. First, this is a picture from the classification dialog, where you can see that if you choose for the yield surface intersection method, he will also display to you on the screen the position of the plastic neutral axis that he has calculated. Okay, but to control these methods inside SCIA Engineer, you have two places. On the left, we have the cross-sections menu, where you can open the classification window that I just shown you. And there you can choose for the three methods, but this only affects the results inside that dialog. So it's just for checking your section even before calculating. If you want to know what the class is, what effect it would have to use another method, you can do it in there without running a calculation or anything. Now, if you want to take this into account into the steel code check, then you need to change and choose the methods in the steel setup, as you can see under classification and then stability classification method. And another small tip so that I can keep talking for the next hour. Okay, I promised you more about Decompose research, and this is the first one of them. It's also the first one that is actually a change of the Eurocode behavior instead of just an addition, something the Eurocode was omitting and that we added some calculations in. And that's Decompose for class 3 sections. When you look at the diagram of the moment resistance that you can use compared to the class of your section, we notice some behavior that's not really feeling natural. Like if you see for a certain C over T value, if you just fall under class 2, you can use the plastic resistance. But then if your C increases by 1 millimeter, maybe you fall into class 3 and suddenly your elastic moment, your resistance moment that you can use drops drastically. Now, can this tiny millimeter change really have such an impact on the section behavior? We feel internally that is not entirely correct, and that's also what the Decompose plus research is going after. So what they proposed, in red, very simplified, a straight line. In reality, it's some nice interpolation curve. It's an interpolation between the elastic and the plastic moment for class 3. So the closer you are to class 4, the closer your resistance that you can use will be to the elastic resistance, and vice versa. If you're closer to class 2, you get something closer to the full plastic resistance. They have calculated out this curve only for I and H sections and for RHS sections. The rules of these interpolations, I will not go into the full detail. They're just formulas, but you can find them on our SCIA help page. A second improvement coming from Semicon Plus talks about the classification limits. They noticed some difference, some discrepancy between the classification limits if you look at the Eurocode just for steel members and if you look at the Eurocode for steel plates, whereas they should be the same. So more research proved that the ones from the Eurocode for members were actually wrong. So they proposed to modify them, adapt them to be correct and to have the same limits for both Eurocodes. This change will actually be part of the next generation of Eurocode as well. And also the rule I explained before about interpolating between elastic and plastic moment for class 3 will be inside our next generation of Eurocode. For now, as they are not technically part of the Eurocode and the Eurocode maybe even prescribe some other way of calculating, we allow the user to choose himself whether or not they want to use it. You can check it in the steel setup. You can approve or not the Semicon Plus method use, and you'll always find the reference at the bottom as well to the research that was used. And this will adapt both the moment resistance for class 3 and the classification limits. So cannot change them separately. It's either everything or nothing. Okay, and the next addition for classification and the final one, I think, is the utilization factor. This one comes from the question, what section class should be used for a stability check? Because if we look at stability, it's an effect that runs over the full length of an element. It's the full column that's going to buckle, not just one section. And if we look at the column in this example, sometimes it has section class 1, sometimes it has section class 4. Which one should we use when we are checking for buckling? That's the question. Now, previously, because there was no guidance, SCIA just used the maximum class found along the member. But our friend Semicon Plus, again, offers another option, which is the use of a utilization factor. We will just look at the section on the element that is being most used, is closest to the resistance values of its forces, and then we use the class of this section as the section class for the stability check. I gave a full webinar about this when we introduced it in SCIA Engineer 21. So if you want more info, search just SCIA Steel 21 on YouTube. You will find it immediately. Again, webinar given by me, so it will be the same explanation as I would give today. I will just go over a bit. It's a bit more fast. In the steel setup, you can choose between the max class along the member or the utilization factor N. And then in the steel check, actually, you can ask to display the utilization values. Here we see that the most used section is at the top. So for this case, we would use a class 1 section instead of a class 4 section for the calculation, which would be a lot nicer, as you can imagine. And that concludes our first round of topics and leads us on to the section checks. The first topic in the section checks is about shear. For the shear, the Eurocode gives us a plastic resistance if the section has a shear area defined, and if it doesn't, it reverts us back to an elastic check of the stresses inside the section. but it only gives us a limited number of sections for which we can calculate a shear area. SCIA, however, uses two more references from which it's found a bunch more of shear areas for a bunch more of shapes of cross-section. They are way too long to put on this slide. You can go to our help web page and they are all on there. You can see for all types of sections, all the formulas that are being used with the source right next to them. Additionally, for the sections that are still not covered by these shear areas, it is also possible to numerically calculate those shear areas. So we can do a finite element calculation on this cross-section and determine a shear area, and still do a plastic shear check for those sections that don't have described shear areas. Whether you want to do this or not is left for us up to the user. This is the option in the steel setup that you can activate or not. Now, this will only influence the cross-sections where we don't have a shear area described. If we have a shear area described, we will always use it. So it's only for the cross-sections where there is no actual description and they are numerically being calculated. On the next topic, this is actually not at all an addition to the Eurocode rules, but it's a reminder for all of you to think about warping when you have some significant torsion in your cross-sections, or when you have torsion-sensitive cross-sections. Because the warping part of the torsion is not considered automatically inside SCIA Engineer. To be able to do this, we should have 7 degrees of freedom, actually, which is the fixity for warping our sections at the both ends of our members. And since SCIA doesn't know whether or not this warping is fixed or not at both sides of our beam, it cannot calculate a warping inside the section. So if you want to consider it, you need to go to the member settings, member buckling settings, all the way at the bottom, activate warping check, and set for the beginning and the end whether or not they are free or fixed for the warping. Also not in the Eurocode is then, but it shouldn't maybe be in the Eurocode. I will add it for completeness here is how we then calculate the stresses coming from this warping. In the first step, we will decompose the torsional moment that's on the elements into standard diagram shapes. Then we use formulas that describe the secondary torsional moment and the warping moment for those standard shapes of torsional, for those standard diagrams of torsion. This will give us the warping moment and the secondary moment. And from these, we can calculate the warping stresses inside the section and do a check of the stresses. And actually, this one will be our biggest topic of the entire webinar. It is the stability checks where we have the flexural buckling, torsional buckling, lateral torsional buckling to be covered. Yeah, I'm sorry, if I don't drink, you will lose me somewhere halfway through this. So, first edition should be known by all of you is the buckling factor. The only way to accurately calculate the buckling factor, unfortunately, is by doing a stability calculation. The best way to deal with buckling factors is to not bother with them at all. Do a second order calculation, put your imperfections, and allow ignoring buckling. And they will always be properly considering the second order effects of your structure. But of course, we don't all have time to do all the nonlinear calculations of immense amount of nonlinear combinations and the imperfections, or to do a stability calculation for every element in your project. And therefore, we need to have some way to at least estimate some k-factors for a simple linear calculation. For us, we have found a reference that gives a good approach, but only for frame structures that have perpendicular connections that are either rigid or semi-rigid. So this is the method used. I think you're all familiar with it. It will have two different formulas, either for non-sway structures, so one that's not susceptible to horizontal displacements, and one for a sway structure. And the k-factors are calculated based on the stiffnesses of the nodes at each side of our element. The stiffness we calculated from two hidden load cases that give us a moment and a corresponding rotation in that node. And if we divide them, we get some stiffness ratio, and this is how we get to estimate some k-factors. But what I want to stress is that this is an estimation, and especially if your structure does not fit the description here, you should really be careful and check the buckling factors that come out as a result. Now, most often they give us a very big result, so that's rather on the safe side, but still, yeah, you should be careful. And then the question maybe you might have is, why do we not have a formula that does a better job at it? Well, it's because we haven't found one yet. So if you guys happen to find a magical formula for it, feel free to let us know. All right, so inside the program, you have the member buckling data where you can choose either to have the software calculate your k-factor or give in your own factor or a buckling length yourself. And you also have at the bottom some additional formulas that we have built in into SCIA Engineer. I think they are for lattice tower structures specifically that you can also be using here to calculate the factor with. And then the sway types, you can also either change them per member in the member buckling data or in the steel setup for all your members at once. Okay, another thing about flexural buckling is the calculation of the uncritical value if we have members with a variable height. Because uncritical is given to us by some of the section properties and then our buckling length, and all of them are quite fixed except the inertia around the axis. This one varies if you have a variable section along the height. So which inertia should we use here to have a critical normal force? Now for this, we refer to the Hirt and Clisnell methods from ECCS, where they find some way to interpolate between the minimum and maximum inertia of the section, but this formula only works for doubly symmetric sections. For other sections, we actually don't have a solution. So currently, it will use the inertia at each section of the beam for the check at that very section, unfortunately. Okay, next on we have torsional buckling and torsional flexural buckling, which are a bit linked. The torsional buckling is pure what the Eurocode states, this formula, and the torsional flexural buckling, the Eurocode actually offers a simplified version of this with some limited application field. So we are going beyond this using a reference from Access Steel, where they do a more full version of the formula, but it will simplify down to the Eurocode one if we use the proper limitations for it. And also another change that we do from the Eurocode for both torsional and torsional flexural buckling is that if you input sheeting on the members, we can incorporate the stiffness of the sheeting into the calculation of these critical forces. And then finally, one that has been announced before, lateral torsional buckling. Also, I put in a quick reminder on what we do in the Eurocode. We try to find some resistance moments considering lateral torsional buckling, where we just take the moment resistance and we multiply it by a reduction factor for lateral torsional buckling. We have two cases, one general case where we calculate the reduction factor based on our imperfection factors of the section and an empirical value, and for rolled or equivalent welded sections where we use the same factors, but also some added factor Kc that accounts for the moment distribution along your member. But the Eurocode doesn't say us how should we calculate M critical. So for this, we reference again to ECCS. We use this well-known formula for the calculation of M critical. Most of the parameters are pretty clear and easy or are easily calculated by SCIA Engineer. So I will not spend too much time on them, but for the rest of them, I will try to give you some explanations on some additional factors. And the first factors I want to discuss are K, KW, and KLT. The factor K in this formula is analogous to our buckling factor. It represents the ratio between our beam length and our buckling length. You can see in the image some standard examples. If the two ends are free, we have a K equal to 1. If they're fixed, we have a K equal to 0.5. Yeah, not rocket science here. The factor KW is a similar one, but instead of buckling supports, we account for the warping fixation. So whether or not the end and the beginning of our beam are free or fixed for warping, again, we range from 0.5 for no restraint to 1 for full restraint. And then we have actually an additional factor inside this formula in SCIA Engineer, which is KLT. It doesn't exist in the actual reference. In the standard reference, this KLT is equal to K. However, in SCIA, we have changed this situation because the length for lateral torsional buckling is not always equal to the flexural buckling length. For example, there can be a lateral torsional buckling restraint that will not restrain the flexural buckling. So in this case, KLT for lateral torsional buckling will not necessarily be equal to K. So our KLT is the same as K, but this time for lateral torsional buckling. Next factors to discuss are the C1, C2, and C3 factors, which account for the moment distribution, the load position, and how symmetric our section is. For this inside SCIA, we have 3 possible ways you can choose to calculate them, but the standard one is this one from the ECCS by Galea. It's also the most known one, I think. For linear moment lines, our C1 is calculated just using a formula, but for point of the line loading, there are different tables, or maybe the graphs are more known. I put both of them on the slide. That will give us the values of C1 and C2. And if we fall somewhere between values, we will do some double interpolation. And then for C3, another table is given where based on C1 value and a value that gives some symmetricity value to the section, we can find a value for C3. So that's the most known of the methods. Second method that we have built in is Lopez, Young, and Serna. When using this method, you should be very careful that the factor C1 is the only one that gets calculated, and the other two are set to 0, which means that if you use this method, you will not account for the load position of your beam, and you will not account for the fact that your section is symmetrical or not. So these will not be considered. However, what it does add is that it uses the actual moment distribution. We will sample the moment value along 5 positions on the beam and use those moment values to calculate a C1 value, which allows you really to take into account some funky moment shapes that are not inside the standard diagrams and to properly account for those. So that's why this method can be interesting. Finally, we have the old method from the precursor of our Eurocode. This is an outdated method which probably shouldn't be used by you today. It gives actually pretty nice, pretty high results for M-critical, but they are not very correct, so you shouldn't be using them. However, if you have an old project that was calculated still with these rules, it would maybe be impossible to make it, to still recalculate it and make it work in current times. So for those old projects, we keep this method alive for you to be able to get back to it if necessary. And again, we get some very simplified tables for simplified bending moment diagrams, giving us some values for C1, C2, C3. All right, this inside SCIA Engineer, you have again the member buckling settings where you can set KLTB, K, and KW. At the bottom, you can set the position of the loads application. And if you would not agree with the method we use for M-critical, you could even do your own user input of M-critical, and then all those other parameters get ignored, and we will use your user value as the value for M-critical. In the steel setup, you can choose the method for the calculation of C1, C2, and C3. I briefly mentioned the additional factor Kc that takes into account the moment distribution for rolled and equivalent welded sections before. In the Eurocode, it already offers some guidance, but again, there are very limited amount of types of moment distributions available. So in SCIA, you actually have an additional option coming from AXIAL Steel, where, well, since C1 is the factor that takes into account moment distribution, from this C1, we can actually calculate a Kc. And if we are using more accurate methods to obtain C1, then of course our Kc will also be more accurate this way. By default, we follow the Eurocode, but if you would like to benefit from this improvement and better taking into account the bending moment shape, you can change it in our steel setup. I already mentioned sheeting briefly when I talked about, what did I talk about? Torsional and torsional flexural buckling. But also for lateral torsional buckling, sheeting can be taken into account in 2 different ways. One way is the sheeting is so stiff that it fully braces the member, it fully stops it from doing any lateral torsional buckling at all. And in this case, we will ignore the check. A second way is that it is not stiff enough, but it still provides us some stiffness. And then we will add this stiffness to the stiffness of the section, the torsional stiffness of the section, inside the calculation of M-critical, higher stiffness, so higher M-critical and a better performing member. We actually reference the Eurocode here. It is used for the calculation of the stiffness of the sheeting. And then the other reference talk to us about how we incorporate it into the M-critical calculation itself. Okay, now that we have calculated all the components, it's time to combine them in a combined bending and axial compression check. Here, actually, we go a bit more severe than the Eurocode. Eurocode only combines the lateral torsional buckling together with the flexural buckling limits, whereas in SCIA Engineer, we will actually check if the torsional buckling case or the torsional flexural buckling case is not more limiting than the flexural buckling itself. And in case it is more limiting, we will actually combine the torsional buckling with the lateral torsional buckling instead of the flexural buckling itself. Finally, we have another combination possible, which is the bending combined with the axial tension. The Eurocode doesn't give a check for this. The Eurocode, this does give guidance in the one for cold forms. We wanted to still consider the effect of combining our lateral torsional buckling with a secondary moment on the section, while considering the positive effects as well of the axial tension. So this is an added check into our version of the Eurocode application. And that brings me almost through the entirety of the topics. And if you made it so far, well, thank you. I have one final extra option, which is an option in the steel setup that is not super known. And that's the moments on columns in simple construction. This option allows you to consider the fact that your beams are not attached to the centroids of your column, but rather to their flanges. And so even if they are connected with a hinge, they should induce some additional moments inside your column. And here, the SCI publication and from Access Steel, we get some formulas to calculate what those additional moments in our columns would be for pinned joints. You can choose to consider these additional moments on your columns by activating the setting in the steel setup. By default, it is off, but there are some limiting conditions. We can only do it for I sections, RHS sections. You should have a structural type column and a structural type beam. They should have a hinge. There should not be 1,000 different beams connecting in the same node, because then he also doesn't know how to calculate this. And with that, you have all made it to the end of this presentation. I think I talked a lot faster than before, but I was catching up for lost time. All the information I gave to you guys today, you can find it on our SCIA help page. It's just help.scia.net. You go to design and check, you go to steel, you go to the theoretical background, and then to the steel members. You will already find some annexes down here, the buckling ratio, the moment factors for LTB, sheeting, everything I've talked about is right here. The standard diagrams for the torque and how the secondary moments are calculated, etc. I only showed you one, but all of them are can be found on here, as well as the references. Or under the Eurocode check, you have another part for the section checks, for example, for SHEAR. As I said, there is the long list of sections with the SHEAR areas and their references that can be found. Really, nothing I said today is something that you weren't able to find already on the help website, which made my preparations a lot easier. But also for you guys, you know that everything is readily available online.